That's
okay,
good.
yeah, now it works finally. Okay, so great to be here. Thanks for the invitation, and I would like to discuss mostly the hard state. The main question of the talk is what is the inner truncation radius in the hard state, and I will not discuss this issues already discussed here, what happens during the transition, during the intermediate state. So evolution of disks and corona in low mass H-state binaries are quite complex, and they go through cycles of quiescence and then outbursts. And then if we consider outbursts, we are more or less sure that the disks are strongly truncated. If they were not, this would disagree with the disk instability model, and the disk extending to the east core could not explain the observed X-ray luminosities in quiescence. As found in many papers, including DB et al. 2001. So the conclusion of those models is that the disk is truncated at about 10 to the 10 centimeter or 10,000 Rg, and a hot accretion flow downstream. And in a paper by Bernardini et al., they found that the width of the H-alpha line implies actually quite large truncation radii for quiescence of V404 Sydney. On the other hand, in the soft state, in the pure soft state, we know that this is at east core. So we now wonder what happens in between. So the quiescence geometry can be shown here. It is truncated disk with some hot inner flow and a weak jet. Then Essin et al. Studied HCJ 1118 plus 480, and 3 weeks after the onset of the outburst, they found about 100 truncation at about 100 Rg based on the strength of the disk black body. On the other hand, there is quite an intense controversy regarding what happens then. This is a figure courtesy of Javier from his paper in 2015 with some of updates by him. And you see we have these two schools. One claims the disk in the hard state is at ISCO, even at very close to ISCO, even at 1% of Eddington. On the other hand, other measurements show it to be about 100. So I will discuss this controversy. And for some years, we have tried to look into this issue. And we had a number of papers on that. We worked with Rupal Basak in 2016. And for GH3-4, the XMM data gave us large truncation radii in all cases. Then RHT PCA, we found that although we can get the truncation radii much larger than RG for actually the same average PCA data, then previous work found that this close to ISCO. Then we look at Cygnus X1 with Suzaku and Newstar, and also found large truncation. Then another paper was with Barbara DeMarco on the black body law constraining the geometry. Then we look at another transient, J1752, and somehow we really were not prejudiced to find truncation. I think this extending to ISCO is much more exciting. I would be happy to find it, but we couldn't find it. And then we look at this famous source, March CJ1820, and again found fitting Newstar data truncation, which I will discuss in a detail. Then we included integral data and found the same. And then in a paper by Marta Dziewak, we found that if you do Lorentzian resolved spectroscopy, then it requires that the continuum is quite complex, at least two zones. Then in a paper by Barbara DeMarco, timing studies of nicer data show quite long reverberation lags, and then again, the interpretation was that truncation radius is large. I would just quickly mention the Lampos model because it was used for MACC. Now, one issue with Lampos is that originally it was used as a simple mathematical description of reflection. You have an axial symmetry, but then it was taken literally. And in this model, 100% of the emission is in the lamppost, and this black body, the black body disk is passive. There are some problems, like pointed out by Dovchak and Don, that a small lamppost cannot intercept enough soft photons. Also, in number of cases, we had quite extreme parameters. Lampposts were found to be very close to the horizon for much smaller rotating black hole. And in that case, there are again more problems. Most of the photons producing this lamppost are light bent and cross the horizon. And for the parameters found above, we find that 100 times more photons cross the horizon than escape. Then we actually need to increase m dot by factor of 100 to make, and then this makes m dot in the hard state much larger than in the soft state, which is certainly not a standard result. Also, the redshift, quite large in this case, time dilation and light bending hugely increase the luminosity in the source frame, and then this leads to runaway production. So I would say lampposts close to horizon are certainly not physical. On the other hand, we can put lampposts somehow higher up, and then in the paper by Doug Pousseau, they fitted new star data with 2 lampposts and found the disk to be close to ISCO. And also they found this disk inclination of about 30 degrees and iron abundance of about 4 to 7. On the other hand, this source is quite well studied, and we have the inclination of both the binary and the jet, and both are in the 60 to 80 region. And also the donor is unlikely to be to have high metallicity. This is quite an old star. It's very unlikely. On the other hand, in our study, we found that there are 2 solutions, actually with great help of Doug. He helped in tremendously showing that indeed there is this low Rin solution and high Rin, and they are separated by a huge wall in high square, which is shown here. We have this low in a reduced solution, and then huge increase of high square, and then a high Rin solution. And this high Rin solution has good features for us because it has inclination of 60 to 70 degrees and iron abundance of about unity. And also, when you look at the predicted spectra, the fit in this paper, the original paper was to new star data up to 78 keV, but there were also simultaneous integral data, and the model with large truncation radius is blue, and you see it agrees quite well with the integral data. On the other hand, the original model has a much higher temperature, and it overproduces soft gamma rays. On the other hand, as I said, lamppost is probably not a good idea. We do see complexity in the accretion flow. We see power spectra that are complex, time lags, and it's very unlikely that accretion flow is as homogeneous as lamppost. And the work by Chris Don and her collaborators also managed to relatively good fits to everything quite rough, but still good as a starting point with 2 zones of accretion, of hot part of accretion, and then cold disk, which is also variable. So then this motivated us to look into models with 2 components for quantization, hard and soft. And we did fit both new star data alone and new star and integral data. And if we include integral data, we find an additional complication that the Maxwellian distribution of electrons is not sufficient. We see a high energy tail going to, in this case, up to 2 MeV. And for this tail, we need to have a high energy tail in the electron distribution. Then in this solution, we found again truncation radius about higher than 20 Rg, inclination of 65 degree and iron abundance of unity and very good fits. Then in the paper by Borrower, DeMarco and collaborators, we look into soft vibration larks, similar to work of Erin. And what she finds is that the larks shorten with decreasing hardness, so which is compatible with both changing corona changing size and the disk becoming more truncated towards softer states. And in that paper, we also look into fitting variable component of the disk black body together with quantization, assuming that this variable component corresponding to reverberation larks is emitted by outside disk irradiated by hot corona, and that values of this irradiation temperature are shown here versus hardness. And then if we interpret this as a disk black body, we find truncation radii of some tens of Rg in the hard state, and then they decrease to ISCO, close to ISCO in the intermediate state. Kara et al. Interpreted those larks as caused by evolving corona at a constant Rin, and the argument was that the iron K alpha component was almost constant in those spectra. However, we look into this issue with new star data, and we actually found the same thing, that if you look at iron K alpha profile reflection profiles, they look very similar for several observations we studied, but in fact, the fits had the inner radius of the disk changing from 10 to 200, and this similarity, just looking by eye, is due to the fact that ionization also contributes, and we do not have extreme relativistic effects. And in fact, we would have extreme relativistic effects if this corona would irradiate the disk ascending to ISCO. We certainly do not see anything extreme in terms of relativistic broadening. So, so then while the larks can be interpreted as either change of the inner radius or the corona height, the K alpha data show the larks are due to moving inner radius. Finally, with Barbara, we were looking into the issue of reprocessing of emission by very compact sources which irradiate disk standing close to ISCO. And when a corona or lamppost irradiates the disk, a part of the flux is reflected as given by the albedo, and a part is absorbed and re-emitted after reprocessing. And then the re-emission is constrained by the black body law, and it has to be, whatever is re-emitted, it has to be emitted above the black body spectrum, which is one corresponding to the most efficient emission, given by this equation, the standard black body law, that sigma times temperature to the fourth equal to the absorbed flux. And then this implies that if the inner radius is at ISCO in luminous hard states, at high luminosities, then the black body temperature is above 1 keV, which is not observed. And this is a figure illustrating that, in which we have, this is effective black body, and this is the reprocessed and reflected spectrum taken from a paper by Zdziarski et al. 2019, and this, the red is the incidence spectrum. And I note that when Revit seal is used for fits, even with its high density version, it still does not get this feature because it's parameterized by the ionization parameter for densities that are still too low to correspond to the true irradiating flux, which can be estimated from the geometry. And then this underestimates irradiating flux, and then this leads to underestimate of the temperature, and therefore one can get a good fit in spite of this problem, but this is not physical. So my conclusions are here. The disk is truncated during the quiescence, and at ISCO in the soft state, and in the hard state, we found the truncation radius is always substantial. And I know that rampos close to horizon are unphysical, and the disk ascending to ISCO in luminous hard state is ruled out by the black body limit. And AHTP will get us much more accurate vibration data together with very accurate spectra, so we can look at it in a few years with, or several years with EHTP. Thank you very much.
Okay, Andre, thank you for your presentation. So the debate continues. Perhaps we can entertain one, maybe two questions.
I think Phil is asking a question, so maybe he can just go ahead and ask.
Yeah, thanks. Hi, Andre. So one of the things is, though, you talk about the reverberation lax, but we see also these leads of the disk versus the power law emission that I showed. And those clearly show that it's the disk emission that has a temperature of 0.2 keV. So you can't put that down to irradiation because it's leading the power law. Now, if you take a disk at 0.2 keV and put it at 100 Rg, that at the ISCO would have a temperature of 1.6 keV. So it would be a crazy high accretion rate. So I don't really see how having these large radii of the disk with 100 Rg that you get from reverberation, for example, on these fits, is consistent with the fact that we see disk variability with the temperature of 0.2 keV leading the power law emission.
Well, I looked at this issue in my HT J118 paper, and I thought that, 1752, and I thought that we found that the accretion rate does not need to be high. So why do you require the very high accretion rates?
Well, because so I think the argument you make that you say, well, it's a radiation, so that's why we can have a high disk temperature here, even from a large radius. But my point is that, but you see that disk varying leading the power law. So that cannot be irradiation. That must be intrinsic disk variability, viscous dissipation, producing a black body emission with this temperature. So it's kind of, it should then follow the R to the -3/4, temperature with radius profile, and then you end up extrapolating that to small radii, and that implies that it has to have a high accretion rate to get that temperature at 100 Rg.
No, I mean, you extrapolate it to low radii if the disk extends to low radii, but in fact there is a loop, as already discussed by Mariano. There is this loop that the outer disk is irradiated and emits seed photons, and then seed photons lead the hard photons, but also there is this opposite situation.
Yeah, but that doesn't have the disk leading the power law. None of this is accounted for in that model anyway. That's a different phenomena where they see the disk lagging. I'm talking about disk leading. I think that's the fundamental problem. I mean, I think it's probably something that we just all need to think about more, but it's just...
The disk, certainly I don't rule out the intrinsic variability of the disk due to viscous dissipation, but I look at that issue. There was this paper by, I think, Judge Steiner, in which they claimed that m dots has to be very high, and this was clearly not correct, because they assumed that the total emission is given by is actually above the truncation radius, but you can also have photons emitted in the hot flow. So I don't get this point. I mean, maybe we can.
Yeah, I think it needs further discussion. Yeah, thanks.
Absolutely. Yeah, so through exchange of emails would be good. So Andreas, thank you very much.
Okay, thank you.